So, in the floating point representation there is one more point regarding this numbers that we are going to store, like in IEEE 754 single precision floating point standard. So, an exponent 255 it indicates a special value. So, if the significant part is 0, so this represent a plus infinity or minus infinity depending upon the sign bit. Okay. So, this has got a special representation of infinity. On the other hand, if the significant part is non-zero, then it means it is a not a number. So, many a time you might have seen while writing programs using floating point numbers. So, it prints the message that not a number NaN like that. So, that actually comes from here. So, if the number that you are getting is of this format, that this the exponent part is 255 and the significant part is non-zero, then it will be telling that it is not a number. And if it is 0, if the significant part is 0, then it is plus infinity or minus infinity depending upon the sign. In the double precision format also, the special exponent value for double precision number is 2047. So, instead of 255, instead it is 2047. So, otherwise it is same. So, if you are getting exponent 2047, then this has got a special meaning. So, this may be, if the significant is 0, then it is plus infinity, it is plus minus infinity depending upon the sign bit, and if the significant is non-zero, then it is not a number. So, this way this IEEE standard, so it has kept special provision for representing infinity and this not a number type of flags. So, another caution that we have discussed in the last class, that both in our model as well as IEEE, so there is plus 0 and minus 0, that representation is possible. So, we should be careful while writing programs and trying to check between whether a variable has become 0 or not, because this plus 0 and minus 0 they are not same. So, you can get some surprising results because of that, either the check may be successful or the check may be may be a failure, though in both the cases the value is 0 only. Okay, but x equal to 0, in some cases the check may be check may come out as pass, some cases it may come out as a fail. So, we have to be careful. So, maybe we will do some other check. Okay. So, we normally what we do is, it is less than some very small quantity. So, maybe I write like x less than 0.10 zeros and then 1. So, that way it is a very small number. So, it may be considered to be equal to 0, the absolute value of x, of course. Next, we will look into how do we do this addition and subtraction in the floating point format. So, floating point addition and subtraction, so we use methods which are analogous to our paper pencil method. So, first of all, the operands must have same exponent, otherwise you cannot do the addition subtraction. So, the exponent has to be preserved, and after doing the addition and subtraction, so we may need to normalize, and that way the exponent may be changing after the addition or subtraction. So, if the exponent requires adjustment, so we do so at the end of the calculation. So, this is the process. Suppose I am trying to do an addition of x plus y. So, if x equal to 0, then the answer is y directly. So, we go back. If the x is not equal to 0, then we check whether y equal to 0 or not. If y is also not equal to 0, then if y is equal to 0, in that case the answer is z. So, it simply goes out. Otherwise, x and y both are non-zero. So, it comes to this point and it checks whether the exponents are equal or not. So, if the exponents are equal, I do not need to do any exponent adjustment. So, I just simply add sign significance, and if the significant becomes 0, then the answer is 0. If the significant is non-zero, then there may be a possibility that significant there is an overflow or there is no overflow in the significant bit containing the number of bits. If there is no overflow, then we have to check whether the result has been normalized or not. That is, after decimal point the first digit should be 1 and all, before decimal point there should not be any digit. So, all those rules. So, it is checking those rules, and accordingly if the results are not normalized, then we have to shift the significant towards left, decrement the exponent part, and that way. So, if there is, so is it resulting exponent underflow. So, if it is not, so we can, and it is result is not yet normalized. So, we may just shift by a number of bits the significant part till the exponent, and go on decrementing the exponent. So, till the exponent becomes this significant is correct as per our rule. So, ultimately when this everything is correct, then we have got the result, then we round up, do a rounding operation of the result, and then it returns. And otherwise, if there is an overflow in the significant part, so we have to shift the significant right, increment the exponent part, and if there is no exponent overflow, then we will go for result normalization and go back. And if this exponent part also overflows, that means after doing this addition, both significant and exponent they have overflown. So, we cannot represent this the added addition result into the given format. So, it will report overflow and it will return. So, there is an overflow in the addition process. Similarly, for the subtraction part, so we just change the sign of y, and then rest of the thing is same as we are doing for the addition part. So, this is simply pen and paper type of addition subtraction. So, that is followed here also. So, suppose we are trying to do this. So, 12 to the base 10 and 1.25 to the base 10. So, this we are adding using 14 bit simple floating point model that we have. So, 12 is represented as in our normalized model. So, it is 0.1100 into 2 power 4, and 1.25 is 2.1 is 0.101 into 2 power 1. So, I have to make both of their exponents same. So, we take both of them to exponent 4, larger one definitely. So, after that, so when this is converted to 2 power 4, so this becomes the representation. Now we add this significant with this significant. So, getting the significant part as this. So, our overall sum becomes 0.110101 into 2 power 4. So, here no adjustment is necessary, because before decimal we have 0 and after decimal we have 1. So, no adjustment is necessary. So, in case of multiplication, so we do similar thing. So, this is also like say paper and pencil type of multiplication that we do. So, we multiply the operands and add the exponents. So, significant parts are multiplied and the exponent parts are added. So, if after that we see, we need to do some adjustment with the exponent. So, we do that adjustment after the calculation. So, this is the multiplication routine. So, we multiply. So, we first check whether x is equal to 0 or not. If x equal to 0, then we say that we check whether we say that the result z is also equal to 0, or if y equal to 0, then also we say that the result z is equal to 0 and it returns from there. And if both are non-zero, then we add the exponent, because while doing the multiplication the exponents will get added. So, we add the exponent and we subtract the bias. Okay. And if there is an exponent overflow, so we report overflow. If there is no exponent overflow, then we check whether exponent underflows or not. In that case, we will report as underflow. In that is not the case, then we multiply the significants, okay, then do some normalization and then do rounding, and ultimately it returns. So, that way this floating point multiplication can take place. So, you can take a paper pencil type of example and see how to do this thing, and I hope you are already familiar with these multiplications from the school days. So, instead of taking the base 10, so it is taking base 2, that is the only difference, otherwise the rules are same. So, another very important issue with this floating point representation is the rounding and errors. Okay. So, no matter how many bits we use in a floating point representation, so our model is finite. So, as I was telling that there is this floating point numbers, they can go up to infinity. So, this after the decimal point how many digits you are keeping, so that way it can go up to infinity. So, that way there will be restriction. Okay. So, we will have to be careful, and then when there is a restriction, so it will introduce some amount of error. So, real number system is infinite. So, our models can give nothing more than an approximation of the real value. So, at some point every model breaks down. So, whatever be the size that you allocate for the exponent part and the significant part, so there will be a limit. So, it will introduce some error. in the calculation. So, if you use more number of bits, then we can reduce error, but we can never eliminate it totally. So, these errors will remain, it will not go. So, how to reduce the error? So, so we will try to reduce the error, or we should be while doing arithmetic with this floating point. So, we should be having an idea like how much error may get introduced into my calculation. Okay. And another thing is that as we are doing some operation repetitively, so this may add increase the error part. Okay. For example, if we are adding all numbers all floating point numbers in an array, okay, then as we are adding successive numbers or successive entries of the array, so this the error also grows. Okay. So, in our 14-bit model, so we cannot exactly represent the value 128.5. So, in binary it is 9-bit wide. So, it is like this. So, in case of floating point representation, what will happen is I have to represent it as this 0.1 something and then 2 to the power some value, but that it will not be possible to represent in 14 bits. So, what will happen is that, so if you represent we try to represent 128.5 in our 14-bit model, we will lose the lower order bit. So, it will become 128 only. So, this 0.5 will not be coming, because the last bit will be ignored, it will not have so much of space. So, the error that is introduced is about 0.39%. So, so if we so just for representing the number, we are losing 0.39%. So, if we go on repeating the process by adding 0.5 to 128.5, so just we go on adding 0.5 to this again and again, then within 4 iterations, so it will introduce about 2% error in the result. So, that will come because of every time we are doing it. So, it is not representable in this system. So, as a result it will introduce some error into the system. So, that is how, so these errors can creep in floating point computations. So, floating point errors can be reduced when we use the operands that are similar in magnitude. So, that is one possibility. And if we are, for example, if we are repeatedly adding 0.5 to 128.5, so it would be better to iteratively add 0.5 to itself and then add 128.5 to the sum. So, what it says is that since every time we are adding 0.5, so you add these 0.5s separately, how many, whatever be the number of 0.5s you need to add with 128.5. So, so many 0.5s are added together and then the resulting sum is added to 128.5. So, in this way, while you are doing this 0.5 additions, so error will not be introduced. So, it is possible that while adding with 128.5 the resulting number, so some error will be introduced, but that will be introduced only once. Okay. So, that way the error caused, so the error possibility will reduce. So, in this particular example, so this error when we are adding 1.5 to 128.5, we lost the lower order bit. But if the values are higher, then we may start losing the higher order bits as well, and as a result we can the situation may become more problematic. So, it may become the number that we are representing may be far away from the actual number. So, floating point overflow and underflow can cause programs to crash. Okay. So, this is there. So, though it is a bit of programming side, but it is important, because if there is an underflow, the number becomes 0, and then when you are doing some division, for example, by that number, so it is a divide by 0 error. So, as a result the program may crash. Similarly, overflow also, it may go out of range, as a result it may generate some wrong values and then the program may crash. So, this overflow and underflow, so these are the two cases, and if we are whenever we are using this floating point representation, so we should be careful, like if you are writing a program, then we should be careful that this type of cases are caught, and then we avoid the operations using those values and come up with, say, some sort of error message. Okay. So, that my the program does not crash or the system does not crash. So, this floating point numbers, so we have to, there are three important terms with respect to floating point numbers: the range, that is the range of values it can represent, the precision, with what precision it can do it, and the accuracy level. So, range is simple. So, range of an integer format is the difference between the largest and smallest values that can be expressed. In case of accuracy, it refers how closely a numeric representation approximates a true value, and this precision means how many the number, how much of information we have about a value. So, apparently it seems that if the precision is high, then the accuracy will also be high, but that is not always the case. For example, suppose we are representing the number pi and we have stored the number as 3.1333. Now, you see that value of pi that we have here is accurate only up to 2 places after decimal. Okay. But while storing it, I am storing value which has got 5 digits of precision. So, 3 1 and this 1333. So, total 5 digits are stored. So, that way the amount of accuracy and the amount of precision, they are not necessarily same. Okay. So, they may be different. So, there are other problems with floating point numbers also, because when you truncate the bits, you cannot always assume that a particular floating point operation is commutative or distributive. Like what we mean by, if I have an operation, say x plus y. Okay, so, this addition operation. So, in general x plus y is equal to y plus x. So, this is a commutative operation, or x into y plus z is x y plus x z. So, the first one is the commutativity property, second one is the distributivity property. So, these operations addition and multiplication, so they follow this type of properties. So, for integers it is true, but for floating point numbers, so it may or may not be true. So, in reality it may not happen because of this accuracy and all. Okay. So, some of the bits may be truncated. So, you cannot always assume that x plus y will always be equal to x plus y plus x, or in particular x into y plus z will be x y plus x z. So, that is another very problematic situation. So, while handling these floating point numbers, so you have to be careful with them. Okay. So, for example, so this a plus b plus c is a plus b plus. So, if you are doing this addition first and then adding c with it, in another case you are doing b plus c first and then adding a with that, then so this is the distributivity property, or say a into b plus c is a b plus a c, as I was telling. So, here this for floating point numbers, so we cannot assume this type of equalities to hold always. Like if you are do a plus b first, so the result may have got some truncations with that c is added. So, on the other hand, when I am doing b plus c first, so this gives another, this may result in some other type of truncation, with that when a is added, the final results may not match of that, may between the two cases. Okay. So, this so another important thing is that when you are checking the value of a floating point number, so we have to say, like, say we want to check, say x, whether x is equal to 2 or not, where x is a floating point number. So, this check may not be correct, because this the number 2 may not be represented with same level of accuracy as x. Okay. So, as a result, what will happen is that even if the mathematically this x and 2 should be same, but in the from the representation point of view, the x and 2, their values may be different. So, while if you put it in a program, so you may find that it is creating some problem. So, it is better that you write it like this. So, absolute value of x minus 2 is less than some epsilon. So, where epsilon is a very small positive quantity. So, we find out the difference between x and 2, take the absolute of that. So, it becomes positive, and then we check whether it is less than epsilon or not. So, this way, so normally in floating point program, so instead of writing it like this, so we have to write it in this format to avoid this type of problems. Okay. So, next that finishes our discussion on this floating point this number system. So, next we will be doing a few exercises which are very interesting. So, the first one, it says that I have got two numbers 75 and 45. Out of this 75 is a base x number and 45 is a base y number. So, what are the possible values of x and y? So, if we want to do this, so let us take this one. So, 75 to the base x equal to 45 to the base y, where this 7 5. So, they are the digits of that number system and they are taken, their numeric values are taken to be equal to decimal 7 and decimal 5. Okay. So, if I just convert it, so it becomes 7 x plus 5 equal to 4 y plus 5. So, that gives me the condition that 7 x equal to 4 y. Fine. So, how can I satisfy? So, any value of x and y that satisfies this equality, so that is good enough for the mathematical point of view. So, we can say that I will choose x equal to 4 and y equal to 7, x equal to 4 and y equal to 7, that satisfies this condition. But this is not a correct result, because if you look into the number here 75 x, so that means this x must be more than 7, otherwise the digit 7 is not defined for x. Because if I have got a base d number system, then the digits are 0, 1, 2 up to d minus 1. So, if 7 is the base, then I will have the digits 0, 1 up to 6. Similarly, for this if so this x equal to 4, I cannot get the digit 7 there. Similarly, if y equal to 7, y equal to 7 is of course all right from the point of view. So, this is fine. So, this does not satisfy the relation. So, what else can be satisfied? So, we can have this the next one. So, I can take x equal to 8 and y equal to 14. So, if I take x equal to 8 and y equal to 14, then it is fine. Okay. So, then this relation is correct. So, we have to, so this is the correct value for this particular problem. Okay. So, we will take another example, say this one. So, 2x to the base 5 equal to 3y to the base 6. So, by a similar logic, so it is 2 into the number is 2 into 5 10 plus x equal to 3 into 6, that is 18 plus y. So, you get a condition that x minus y should be equal to 8. So, if I put any value of x and y such that x minus y equal to 8, then we are done. So, can I take say x equal to 9 and y equal to 1. So, that satisfies this relationship, but the problem is this one. So, this y should be at least y should be less than 6 and this x cannot be 9. So, x cannot be 9. So, x has to be less than 5. Okay. So, x has to be less than 5. So, naturally, I cannot have any relation that satisfies this particular property. So, I cannot choose any value of so, if I choose y equal to 1, then I will require x equal to 9. So, which is not possible. So, I can choose x at most equal to 4, fine. So, x at most, since this is 5. So, I can have x to be at most equal to 4. So, if I put x equal to 4, okay, so 4 minus y equal to 8 or y also equal to 4. So, that is a possibility. So, I take x equal to 4 and y equal to 4. So, 24 to the base 5 equal to 34 to the base 6. Is it correct? So, 5 into 2 10 plus 4, sorry, then of course, so this x minus y, no, sorry, this is not correct, because this 4 minus y. So, y is becoming minus 4. So, so I cannot choose any value of x and y which satisfies this relationship. So, this I cannot get any satisfying value for this problem. Okay. Then this one, the third problem is simple. So, here we have got 32 to the base 9 and 24 to the base 5. So, you multiply them, and then so for multiplication purpose. So, you can first convert both of them to their decimal values, do the multiplication and then convert it into a base 6 number system. So, you have to go on dividing the number by 6 and see what are the remainders, and then the remainders you can represent it like that. Then the fourth one, this 267 to the base 8 in the base 11 number system. So, here first of all this 267 to the base 8. So, this has to be converted into decimal number system. So, this is 2 into 64 plus 6 into 8 plus 7. So, that is 128 plus 48 plus 7. So, that is this is 55. So, 55 plus 128. So, 128 plus 55. So, this is 183. So, we get 183. Now, this 183 if you divide by 11. So, it is 1 then 7. So, 6. So, 66. So, then there is 73. So, this is your 7, then again by 11. So, you get 1 and 5 and then 11, 0 and 1. So, 157 in the base 11 number system. So, this way you can convert numbers from one number system to another using this division. Okay.